Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's lecture. So in the previous lecture we have seen how we can, given a transfer function, sort of split it up into sum of partial fractions, right? And of course the idea was that that partial fraction expansion would enable us to get the inverse Laplace transform in an easy and convenient fashion. So today we shall take off from there and then we shall see how to take the inverse Laplace transforms of certain transfer functions which may appear on the face of it a little more difficult to handle than what we have seen so far, in the sense that the poles of those transfer functions may not be necessarily real. We shall see that in exactly the same fashion as we treat real poles, we shall be also able to tackle complex poles as well, right? And subsequently we shall move to somewhat less abstract domain, in the sense that right now we are looking at differential equations. We are not questioning ourselves as to where these differential equations are coming from. So the goal is to finally converge on some practical systems such as electrical circuits. We shall see some other systems later on, but today we shall introduce the application of Laplace transforms in solving electrical circuits. Some of this might be familiar to you from an earlier course or exposure to circuit theory. Nevertheless, we shall try to highlight certain key aspects which will be useful for this particular course. So without further ado, let me get started. If you recall, in the previous lecture we had taken a differential equation that looked somewhat like this: x double dot plus 2x dot plus x is equal to 0, with x dot, the initial condition of x dot being b and that of x being a. And we saw that if we apply this Laplace transform to this differential equation with zero forcing function or no external excitation, just leave it to behave autonomously to its own non-zero initial condition, right? So we know that this is called the zero input response of the system, as we've defined in the previous class, right? And we saw that we can actually solve it and get an expression that looks something like this. Now the obvious question is, once we've done this, how does this help us in getting the inverse Laplace transform? So let's see where this allows us to go. So now, having expanded this expression xs in the partial fraction like so, we can then write that x of s is given by nothing but a over s plus 1 plus a plus b over s plus 1 squared. Now how does this help us in getting the Laplace inverse? Because this, you see, these sort of expressions are straight away available in the inverse Laplace table. In fact, we do well to remember these sort of results, and I am sure that after having practiced a number of problems in this of this kind, these will seem very familiar. So let's just apply Laplace inverse on both sides, and then what we have is, because the Laplace transform as well as its inverse is linear operation essentially, we can say that the Laplace inverse of the sum is the sum of the Laplace inverses, right? So in one step straight away I am going to write it in this fashion, right? And now of course we know that the left hand side is nothing but the x of t that we seek as a solution to that differential equation, and the right hand side will tell us that this is nothing but a e to the power minus t plus a plus b times t e to the power minus t. So this t comes in because of this squared term below. Okay, so whenever we have these repeated poles, we have some powers of t appearing. If you recall, we had actually derived this a few slides back when we saw, we expressed that integral as I of k, right, and we saw what it entailed. So let me just go to that particular slide just to refresh your memory. Yeah, so this is the slide where we saw this I of k. Yeah, this is a recursive relation, and we derived this relation here, that I of k is nothing but factorial k divided by s to the power k plus 1, right. Okay, so we are putting this to good use here, and we see that eventually expanding into partial fractions allows us to get the solution quite simply without avoiding any steps that you have learnt in calculus, such as integration, right, and that is the benefit of using Laplace transforms. Now you see, how did we actually derive this here? In the previous class, if you see, we equated coefficients. Needless to say, equating coefficients always works. So if you've forgotten every small trick, maybe 10 years down the line, you've forgotten all these parlor tricks that people teach you in those textbooks, right, not really parlor tricks, but some shortcuts, you just equate coefficients. How's that? You have this x of s given by this, so multiply, cross multiply on both sides by s plus 1 squared, or whatever is in the denominator, right, and then you will have one polynomial on the left hand side, another polynomial on the right hand side. You equate the coefficients of the polynomial, s squared, s, 1, s cubed, whatever appears, yeah, and if you equate those coefficients, you will have exactly n plus 1 equations, alright. You will have n plus 1 because an nth degree polynomial has all the powers of s from 0 to n, right, and solving those n plus 1 equations, you can actually find out each one of these coefficients, right. Yeah, so there are of course shortcuts, simpler techniques to do this, and we have seen some examples of this. Just to apply that same trick here, not to belabor the point way too much, but let us say we again try this with a1 by s plus 1 plus a2 by s plus 1 squared, alright, and let us say we want to find out, determine the coefficients in exactly the same fashion as we did here. We should get the same coefficients, right, if we are, this is our xs, it does not matter what method we are using. So then what you do is, you multiply both sides by s plus 1 squared, so you take s plus 1 squared times xs, and that will give you a into s plus 1 plus, so a1 into s plus 1 plus a2. Now if you apply, pass it through the limit s tending to minus 1, of course this vanishes, this goes to 0, needless to say, and this remains a constant because this is independent of s, right. So therefore what you have is a2 straight away given by limit s tending to minus 1 s plus 1 squared xs. And what is this xs? Just to remind you, we have this xs given by this. So if you just plug in s is equal to minus 1 over here, yeah, you can get this value. So I know we have discussed this in the previous lecture, but just to connect the thread here, we can do this. We are redoing this, okay. And then if you now want to find out the next coefficient a1, there you can quite simply apply the equating of the coefficients straight away, right. So what you then have is, notice here, a1s plus a1 plus a2, yeah, that is equal to nothing but, let me recall this, as plus 2a plus b is equal to as plus 2a plus b. So whichever one is easier to solve in which manner, we will use that. For instance here, to get a1, we do not actually even need to bother with the second part, you see, yeah. In order to get a1, we can just equate the coefficient of s on both sides and we get straight away a1 is equal to a. We do not have to bother actually, it is a hybrid method. In the first part, to get a2, we just use this expression. Of course you can just use this to get both a1 and a2, but this actually helps as I told you earlier, we always want to decouple equations. When we have simultaneous equations in multiple variables, we want to decouple them. So this actually aids us in doing that. Anyway, now we look at something slightly more complicated, although not very difficult, I would say. What if your poles, instead of being real, like in this case, yeah, or even in the preceding example for that matter, for example here, you had distinct poles but they were all real. What if now you end up with a transfer function which has actually complex poles, right? So for example, let the numerator be anything, I don't care really at this point, but the denominator looks something like this, right? Let us say this is my g of s. How do I expand this? Now if I want to expand this, quite clearly I can always do this. There is no reason to suspect that this won't work for complex numbers. Only thing is, look on the left hand side, each of these terms a, b, p, q, they are real. So we typically want to expand in partial fractions but also want to keep them restricted to real numbers. That is what actually holds us back. But if we expand our horizons, if we do not have any such inhibitions, and if we say I do not care, I have learnt one method, I am going to push it through every time I encounter a transfer function which I have to expand by partial fractions, I am just going to apply it blindly. Then all that you need to do is get yourself out of this domain of real numbers and say that I am going to expand it in this fashion. So I am going to just say z1 by s minus p1, or maybe let me not call it z1 because later on we will define zeros as z, right. So let me call this say k1 plus k2 by s minus p2, where instead of real we now allow k1, k2, p1 and p2 to be complex numbers. Something beautiful will happen, something beautiful will emerge out of this. If you now allow them to be complex, let us say, then k1 can be written as k11 plus, let us say we have, yeah, so basically we are trying to expand this into two real and imaginary part. So since k1, yeah, so since k1 can be expanded into two parts, k11 is the real part, and then we have plus j k12. So you can also use I. Normally in electrical engineering in most cases we use j, and in this course we shall throughout use j as the square root of minus 1, the imaginary number. And let us say k2 is equal to k21 plus j k22. Okay. Now k11, k12, k21 and k22 are all real. Okay. So now the claim is that k1 is equal to k2 conjugate. Okay. It is not very difficult to see, I will just point you out to how this can be easily seen. In other words, this means that what we are claiming is that k11 is equal to k21 and k12 is equal to minus k22, right. So now how do we see this? You see, again you apply the same technique, exactly the same technique. What is that? So you take gs and multiply this by s plus a whole squared plus b squared. By the way, what is p1 and p2? If this is your quadratic polynomial, it is needless to say that, please note, I am going to make a side note here, of course this is a quadratic equation, so you know that the roots are minus a plus jb is equal to p1, you can interchange p1 and p2, and minus a minus jb is equal to p2, alright. So now we are going to just multiply this on both sides, and what we will then end up with is k11 plus jk12, that is basically k1, times s minus p1 into s minus p2, but the s minus p1 gets cancelled here. So we just left with s minus p2, which is s plus a minus JB, right, and then plus this K2, which is nothing but K21 plus JK22 times, and now we have S minus P2 gets cancelled from the overall product here. So we are left with S minus P1 on top, which is basically S plus A, okay, this was S minus P2, right, so this should be plus. So this is S plus A minus JB, right, and now all that we need to do is we need to equate the coefficients. So what is this? This is nothing but it is going to give us PS plus Q. Remember, P and Q are real numbers, and that is basically what is going to prove to us that K1 and K2 are complex conjugates of one another. I will show you in a bit. So now what is this? Look at the coefficient of S. On the left hand side the coefficient of S is real, so on the right hand side also the coefficient of S must be real. On the other hand, if I have written this K1 and K2 as complex numbers, then obviously there will be some imaginary part that is also appearing as the coefficient of S. I must equate that to 0. So what is that imaginary part? Let me just quickly write down this K11 plus JK12 S plus K21 plus JK22 times S, alright. So clearly you see, if the coefficient of S has to be real, then K12 plus K22 must vanish, because that is the imaginary part of the coefficient, right. So I am not going to write this in a very structured way because I am not really in the business of doing proofs here, but you can see as we write in the next slide that because P is a real number, therefore the coefficient of S must be real, and therefore the imaginary part of the coefficient on the right hand side must vanish, which dictates that K12 is equal to minus K22, which is basically the second part of what we wanted to show. What about the other part? Look, remember that Q is also real. Now if Q is also real, then the constant term that appears on the right hand side, the imaginary part of that constant term must also vanish. But what is the imaginary part of the constant term? That is slightly more involved, not very difficult, it is just a product of complex numbers. So we have here K11 plus JK12. If you do this very carefully, you will see that this is A plus JB, right, plus K21 plus JK22 times A minus JB, right. So this entire term must also be purely real. So what is the imaginary part? You see K12 multiplying with A, yeah, and K11 multiplying with B, plus K21 multiplying with A minus K22 multiplying with B. That seems like too many terms, no? But we already know this from the first part, so we are going to apply this, okay. If we know that K12 is equal to K22 minus K22, then look at what happens here, minus K22B, yeah, so we have a minus K22 times B appearing here, and we have a plus K12 times B appearing here, so that part, K12 times A appearing here, yeah, so those parts will definitely vanish. Let me just expand it out instead of just doing this in a hand waving fashion. So we have basically, let us look at the Q is equal to the constant term is equal to, on this side what we have, K11A plus K21A, K11A plus K21A, that is of course purely real. What about the imaginary part? Okay, we will also have a couple more real parts, so it is minus K12B, minus K12B, because J squared is minus 1, so minus K12B, and this is going to be plus K22B, plus K22B, but this is already going to vanish, you see from the first part, K12 is equal to minus K22, or is it going to vanish? No, it is not going to vanish, it is going to remain here, because these are equal. But what about the imaginary part? This is all about the real part. What about the imaginary part? If I multiply this here, you see that you get A times K12 plus B times K11 A times k12 plus B times k11 minus B times k21 minus B times k21 minus B times k21 plus k22 times A plus k22 times A. Now you see here k22 plus k12 times A, this vanishes. Why? Because we have already seen that from the coefficient of S this part must vanish. So we have already satisfied this. Therefore, this and this we can cancel out, right. What we are left with then is this part, of course, times J, but we know that this must vanish. If this must vanish, then we are basically left to conclude that k11 is equal to k21, which is what we wanted to prove in the first place. So therefore, although it is not a big deal and anyone can prove this, but the point is that when you are expanding, even though this appears like there are 4 terms here and there are only 2 terms expanded by partial fractions, essentially because of the fact that k1 is equal to k2 conjugate, you are still left to deal with only 2 unknowns. So what you have to equate and get from both sides are essentially 2 unknowns. Once you know k1, you know k2 completely. Why? Because k1 and k2 are complex conjugates of one another. So that problem of dealing with too many variables that might appear at this point is basically not a problem at all. Okay. So let us take this, carry this a little forward and see where this leads us. It is all very well and good to say that yeah, we can expand this in the same fashion as we expanded our transfer functions with real poles, but does it really help us in the end game, which is essentially to get the inverse Laplace transform? See, in what form will we get this eventually? Once we have expanded this in this fashion, yeah, what we will get is finally, therefore, let us say we take the Laplace inverse of G here, then what we get is Laplace inverse of k1 over s minus p1 plus the Laplace inverse of k2 upon s minus p2, yeah. And if I do not care about the fact that this is complex and both k1 and p1 are complex, I can just use the same result that I had used earlier, which is that this is going to be nothing but k1 e to the p1t plus k2 e to the p2t. But here is the problem. When we are dealing with real systems whose differential equations have real coefficients, people are sometimes, I mean, for all practical purposes, so far as we are concerned, this is a valid legitimate solution to the differential equation that we sought to find, or to the transfer function whose Laplace inverse we were trying to find out. But people might nitpick and say, well, I gave you a transfer function containing only real coefficients both in the numerator and denominator, and you are giving me an inverse Laplace transform which is all this complex number business, and I do not like this. Yeah, why don't you massage this somehow and get it down to real numbers, which helps me to relate with what I understand. I am not comfortable with seeing these complex expressions. You give me this k1 which is a complex number, this p1 which is a complex number, k2, p2 and so on and so forth. It is a different matter that k1 and p1 are basically complex conjugates of k2 and p2 respectively, but nevertheless they are still complex numbers and I am not comfortable. What if someone says that? How do we go about this? Well, it is not very difficult. So you see, we use the fact that this expansion gives us essentially k1 e to the p1t plus k1 conjugate e to the p1 conjugate t. I am using the star to denote a conjugate. So let p1 is equal to alpha plus j beta, therefore p1 conjugate is equal to alpha minus j beta, and let k1 is equal to, okay, let me just use a and b instead here, instead of that k11, k12 and that cumbersome thing. So let us say this is a plus jb, and k1 conjugate is then clearly a minus jb, right. and if I do that, then this expression turns out to be nothing but a plus jb times e to the alpha t e to the j beta t plus a minus jb times e to the alpha t e to the minus j beta t, right. You can always do that because alpha plus j beta can be written in this fashion. Products, we know we can split the indices like this. So therefore we can take e to the alpha t common out of this, right, and we have a e to the j beta t plus e to the minus j beta t, okay. Let me just adjust by 2 here, plus jb, excuse me. So this is jb by 2, and I write this as e to the j beta t minus e to the minus j beta t. So 2b by b, right. So now how does this help, you might ask, right? How does this help? So then we pull it out, e to the alpha t out as usual, and let us say we pull out the 2 also, yeah, we pull out the 2 also here. Then what are we left with? So we are left with a, and notice what is this? This is nothing but cosine of beta t, isn't it? What about this? Yeah, what about this? Well, this is nothing but, if I push the j in the denominator, then I have j squared b e to the j beta t minus e to the minus j beta t, and I have 2j. But what is this 2j after all? This whole term, this is nothing but sine beta t. So therefore we end up with e to the alpha t, and we have a cosine beta t minus b sine beta t, right, and there we have it. So I have shown you that even if you have transfer functions which have complex poles, you apply exactly the same method, viz. Equating coefficients, right, and you will still end up with something that looks like this. If you are uncomfortable with this because it only contains complex numbers as its coefficients, you can always carry out this expansion and eventually you end up with an expression like this. Of course you can take this even forward, right, you can take this even further and you can just say, well, I am going to just say square root a squared plus b squared, right, and e to the alpha t, and you can always say this is cosine beta t into a over square root a squared plus b squared minus sine beta t into b over square root a squared plus b squared. Why does this help? Because now you can call this as cos phi and this as sin phi, right. So let a over square root a squared plus b squared equal cos phi. Legitimate, no? It is less than 1, so it can always qualify as cos phi, alright. So then what you have is cos beta t cos phi minus sin beta t sin phi, which if I take just one more line will end up with square root of a squared plus b squared into e to the alpha t into nothing but cosine of beta t plus phi, right. So I have everything I needed. This expressed completely, right, this expressed completely in terms of real coefficients, real numbers, no complex number business, and now people should be reasonably happy with this. On the other hand, if you recall, there is another way of doing this, maybe a bit of stress on your memory, but if you recall in the Laplace transform table that we had seen a few lectures back, we had seen that Laplace inverse of omega over s squared plus omega squared is equal to nothing but sine omega t, and similarly Laplace inverse of s upon s squared plus omega squared is nothing but equal to cos omega t, right. Now we use the complex shift property to show that omega over s plus a whole squared plus omega squared is equal to nothing but e to the minus at sine omega t, right. Same thing applies for the, sorry, no, this is a cos, this is going to be a cos, excuse me, it's not really sine, it's going to be cos, let me correct that, yeah, right. So same thing we can, or is it, no, it's going to be sine, right, that was my bad, yeah, it's going to be sine, that's right. So the same thing you can apply the complex shift property. Now notice, what about this transfer function? This transfer function looks exactly uncannily similar to what we had here in the first place, right, when we are dealing with this. So you see one of them has s, which is clearly related to the cosine term, the other does not have s, so you obviously have to adjust by b in the numerator and denominator to get this exact form, right. So you can just say ps upon b, so you pull out p by b common and then you write, no, in s you do not need to do that, so you can just pull out p common. In the second term you just pull out q by b common and you have a b on top here, right. So then straight away you can just apply this complex shift property to this Laplace inverse and you will get the answer. It will be nothing different from what we have obtained, by the way, right. So you will have the sum of a damped, so-called damped sinusoid and cosinusoid, okay. And again, if you want to write it as a single term, you can always write it in this fashion, right. Okay, so let us take another look at an example, a concrete example of this type. So suppose we have not just this complex conjugate poles, but also another pole at the origin, alright. So we know that we can write this, of course we can write this as k1 upon s plus k2 upon whatever this is, s minus p1, so k2 is a complex number, of course this is a real number, plus k2 conjugate upon s minus p1 conjugate, right. Now here you might see, you might get a little tired here by this time, right, yeah, this is too much work, I have to again multiply both sides by everything and then apply this limit and then evaluate all those things. I know I have to only find out two variables which constitute k2, but still you might be a little reluctant, you might say, isn't there an easier way out? After all, once I get into this complex number business, I have to again bring it back to the real number business, right. Suppose you do not want to remember too much stuff, is there a shortcut to this? So instead of generalizing this method, I will illustrate this through an example. Again, this hybrid method will serve us very well. So let us apply s tending to 0, s times gs. What is that? I am just cross multiplying by s on both sides, so this s vanishes. So on the left hand side I have this, I have 3/5, right, and on the right hand side I have limit s tending to 0 k1 plus k2 s upon s minus p1 star, sorry, p1 plus k2 star s by s minus p1 star, right. So now if I let s tend to 0 here, I will be only left with k1 is equal to k1. So basically I have already solved this, so I have got already k1 is equal to 3/5. Now suppose I am reluctant to write it in this fashion. If instead I want to retain this in its real terms, then what is the real partial fraction expansion of this? The real partial fraction expansion, we have already seen this in fact. Real partial fraction expansion is nothing but what we started from, which is something that looks like this. I am afraid this is the only real partial fraction expansion that you will get for a complex conjugate pairs of poles, yeah. Only if you expand this further into this fashion will you get complex numbers. If you want to retain the real numbers only, then this is as far as you can go, right. So the general expression then for this will be like Gs is equal to K1 upon S plus K2S plus K3 upon, what is the denominator, S into S squared plus 2S plus 5. S into S squared plus 2S plus 5. Right. So now if we have already found K1 from here, it does not make sense to keep this as an unknown, right. So what we do next is we multiply both sides by, sorry, not this, this will just remain this, yeah. So we multiply both sides by S into S squared plus 2S plus 5. So then on the left hand side we get just 3. So we multiply both sides by S into S squared plus 2S plus 5. We go back to our same old tried and tested technique of equating coefficients, you guessed it right. Okay. We have this, and then we have K1 times S squared plus 2S plus 5 plus K2S plus K3 times S. But now we do not need to pretend as if we do not know K1, right, because we have already evaluated K1, we have done the hard work, not really hard work, but we have actually done the work of obtaining K1 in this step, right, by just multiplying through S only. So the trick I would like to point out here is, if you have combination of complex and real poles, first multiply it out with real poles one by one unless they are repeated, and then you see what those coefficients of the real expansions are, that is in this case this K1 or terms like so, right, and then you multiply by the overall denominator and equate coefficients and use the fact that you have already determined what K1 is. You need not, of course you can just equate from both sides here and you will get K1 plus K2 is equal to 0, and you can pretend that as if you do not know that, but we do not need to pretend that, that is what my claim is, right. So having gone through this step, we can now straight away see that from here, if I plug in K1 is equal to 3/5, then you will see that K2 I can evaluate as, I believe, as minus 3/5, right, and then in the expansion you see if you apply this as 3/5 you already get 3 here, so the constant does not need to be equated, the only thing you have to now equate is the coefficient of S. So what is that? That is basically 2 K1, which is 6 by 5 plus K3 is equal to also 0, so you get K3 is equal to minus 6 by 5, and once you have expanded this, as I said, now you can just apply this other technique, this technique, the knowledge of the fact that we can straight away read off the inverse Laplace of terms or transfer functions that look like this, or rational expressions that look like this, right. So we are done. So I hope that with this you are at least convinced that even if you are faced with poles that are complex, there are at least multiple ways, and this should not actually be a deterrent, this should be actually easy as pie. You either equate coefficients, or you use those shortcuts, or you use some clever manipulation like hybrid methods, like in some coefficients you evaluate using the limiting condition, that is you pass it through the limit, and some other coefficients you equate the coefficients of the polynomials on both sides and you get those other terms like K2, K3 here, right. So there are multiple ways of doing this, do not confuse the different methods, but if you have a certain number of unknowns on one side of the equation, I hope that by now you are convinced that there are several ways of solving for them. So basically taking inverse Laplace at this point should appear pretty straightforward and routine, and that is essentially the goal of this discussion that we have had so far. Before we wind up with this discussion on inverse Laplace transform, there is a couple of things that I need to mention. Now so far we have only discussed about Laplace transforms of rational functions, where the numerator and the denominator were both polynomials, but remember that you could also have terms like e to the minus s tau appear in your transfer functions, right. In that case your transfer functions will not be rational. wherever you have this e to the minus s tau making its appearance in a transfer function, you can forget about the transfer function being rational. Why does this appear? If you recall, this had to do with the shift operation, the time delay, right. So if a signal is delayed by tau seconds, then you have this e to the minus s tau appearing in the frequency domain, in the Laplace domain, right. So that is what causes this. So a quick example would be like if you have water running through a pipe, right, and the velocity of the water flow through the pipe is v and the length of the pipe is L, then as soon as you turn on the knob here, you don't have water flowing out of this, right. The time it takes for the water to flow between the knob being turned on and the water to flow out from here roughly can be estimated. A very rough estimation would be L over v seconds, right. So that is where you might model this as a shift, a time delay of e to the minus L by v s, okay. So this does appear in time delay systems and you will be faced with these. What do you do then? Again, instead of generalizing this, I believe that nothing speaks better than an example. So how will you do this? I will not solve this example completely, I will just tell you that you have some, let us say minus 2s plus 3s e to the minus 5s, you can have multiple such terms, right, multiple coefficients of s in the exponential, and let us say the denominator is s plus 2 into s plus 3 into s plus 7, okay. The standard expansion for this sort of a partial fraction expansion for this sort of a transfer function would be like this. So you club together all terms related to e to the minus 2s and you expand them as a over s plus 2 plus b over s plus 3 plus c over s plus 7 plus e to the minus 5s upon d over s plus 2 plus e over s plus 3 plus f over s plus 7. And once you have done this, all that you now need to do is, see what is the trick here, then basically pull out these time delay terms and their associated terms together, right. So this can be written as basically 2s e to the minus 2s upon whatever terms are here plus 3s e to the minus 5s upon whatever terms are here. Call this one like G1 and this one G2. Now forget about the fact that you have these time delays making their appearances here. Treat this as if this is the partial fraction expansion of G1 and treat this as if this is the partial fraction expansion of G2. Remember that G1 and G2, of course this is sans this time delay here. So when I am saying G1, I am only referring to the rational part. When I am saying G2, I am only referring to the rational part without the time delay, okay. So this is G1, this is G2, okay. So now treat this as an expansion of G1, treat this as an expansion of G2, which we already know how to do, irrespective of whether these fellows are real or complex or what have you, right. Once you have done that, then you can take the Laplace inverse on both sides, of course keeping in mind that the Laplace inverse due to this e to the minus 2s will lead to a shift or a time delay in the time domain, right. So that is the crucial aspect that one needs to remember, okay. So now having seen this, we will summarize whatever we have seen so far in a sort of a concise statement, not really a summary of partial fraction expansions, but we will draw a picture of all the different types of poles that we can have in a transfer function. So say this is the Argand plane, this is the real axis, this is the imaginary axis, alright. And once we have seen this, what can we now say? Suppose we can have a pole here and we can have a pole here. What are these? These are positive real poles. So what is the response due to this? What is the Laplace inverse of a term such as k by s minus p? We have already seen that this Laplace inverse is nothing but k e to the pt. Now if p is positive, then you can imagine that the time domain function would blow up like this. What about this? This is, let us say p1, this is, let us say p2. What I know from this picture is that p2 is greater than p2, p2 is greater than p1, sorry, which means that this will rise faster, this will blow up faster at a faster rate, because this is a much more rapidly rising exponential. Similarly, if you have real poles on the negative real axis, then of course this will decay. If you move more and more to the left, then that same term here will decay even faster. Okay. What about something that's on the origin, that's at the origin, a pole at the origin? It will be a constant term. So basically the picture for this will be some constant level. Whatever you had at the initial condition, that level will be held. Okay. So remember, what we are trying to find out is the response due to non-zero initial conditions only. There are different notions of stability. Here we are talking about stability as in, given that there is no forcing function. When there is a forcing function, then we need to bring in the notion of Bibo stability, which is basically the short for bounded input, bounded output stability. We will talk about it a few lectures later. For now, we are just talking about the stability of the system with respect to its response to non-zero initial condition, that is the zero input response. Okay. So suppose you have non-zero initial conditions, then whatever your initial condition was, it will be held at a constant level if there is a pole at the origin. If there is a pole on the right hand side of the real axis, then it will start blowing up from its initial condition. If there is a pole on the negative real axis, then it will decay from its initial value, right. So these behaviors are clearly termed as stable, these behaviors are clearly termed as unstable, this behavior is termed as marginally stable. Of course, you can also have conjugate poles like so. As we have seen, we have complex poles and zeros as well. So you can have conjugate poles here. What happens then? Of course, their Laplace inverse corresponds to pure sinusoids or cosinusoids. So these are oscillatory. Okay, this is oscillatory response, and this is also termed as marginally stable. This is also termed as marginally stable. So there is no difference between these two responses essentially. Yeah, these are oscillatory response. So the level is held constant. On the other hand, if you have complex conjugate poles like these, the response due to them would be again sinusoids, but with decaying amplitudes. So the envelope, this is called the envelope. So the envelope would be a decaying exponential. So this will still be oscillatory, but it will keep decaying. So this is still well within the definition of what we call as stable behavior. Yeah, right. Similarly, if you had suppose conjugate poles on the right hand side, then it will be a diverging sinusoid or cosinusoid. Yeah, the amplitudes would keep increasing. So this is again clearly just like poles on the right half of the real axis. This will also lead to unstable behavior. These are exponential envelopes, by the way. This, yeah. So again, you will have responses like these. Sorry, this should be touching here. Yeah. So all this seems well understood, but there is a catch. The catch is that if you have repeated poles on the imaginary axis, then the story changes. All right. So far we have seen that anything to the left of the complex plane, right, left half of the complex plane, left of the imaginary axis, any pole that lies on left of the imaginary axis leads to decaying behavior. Whether it is oscillatory decay or a pure decay depends on whether the poles are complex conjugate or real respectively. Similarly, anything to the right, the judgment is clear, it is going to be unstable depending on whether it is real positive or on the right half complex conjugate, it will be either purely divergent or oscillations along with the divergent behavior. But it is this curious case of poles on the imaginary axis where the jury is still out. What is it? If you have non-repeated poles on the imaginary axis, then the picture will be exactly as I have drawn here. On the other hand, if you happen to have repeated poles here, what happens? Just recall that if you had terms like k over s plus p, or sorry, s minus p whole squared, if you have terms like k over s minus p whole squared, then the Laplace inverse of that happen to contain this t e to the pt. Now you see, if this p is a complex number on the left half plane, then there is still a decaying part to it. So this is some alpha plus j beta where alpha is negative. This is some alpha plus j beta where alpha is positive, right. So even if you have multiple poles on the open left half, which is to say excluding the imaginary axis on the left half side, or the open right half, which is again excluding the imaginary axis but purely on the right hand side of the complex plane, the behavior of the system, the qualitative behavior insofar as stability is concerned, does not change. After all, the exponential, when it is a decaying exponential, is way too powerful compared to any polynomial. So whether it is t, or if you have a cube, then it will be t squared. So if it is, let us say, t to the k here, then this will be probably t to the k minus 1 here. So the exponential decays faster and rises faster than any polynomial. So it is basically the behavior of the exponential that will determine whether the overall response is going to decay or blow up as time t goes to infinity, and that is going to govern the stability. If it decays, then it is definitely going to be stable. If it blows up, it is going to be unstable, right. So therefore, I do not mind if I have repeated poles on the open left half or on the open right half. I can blindly say, if all my poles, irrespective of whether they are repeated or not, if they are on the left half plane, the system's behavior will be stable, the zero input response of the system will be stable. Similarly, irrespective of the multiplicity or the number of repetitions of each individual pole, they need not be distinct. If all my poles, or even if one of my poles is on the right half plane, then my system's response will blow up. Even if one pole is on the right half plane, it will blow up, because even if the other modes decay, that one mode will keep blowing up, right. So that is also another key concept, by the way. It takes just one bad apple to spoil the party, right, one rotten apple, which is to say that one pole on the right half plane is enough to qualify a system as unstable. On the other hand, in order to qualify as stable, you need all of your poles to be on the open left half plane. If there are non-repeated poles on the imaginary axis, then you can still call it marginally stable. Coming back to the question, now what happens if there are repeated poles on the imaginary axis? What about a point on this imaginary axis? This is a pure imaginary part, no? So this will only contain a j beta with no alpha. So now think of this, you basically have a term like t to the k minus 1 and e to the j beta t. What is this? There is no decay now. So it is only going to be a sinusoid with an envelope that, though not exponential, is a linear envelope. So the response would be something like this. It would still be a divergent or oscillatory divergent behavior. The envelope now would be a straight line, or if k is greater than 1, it will be a polynomial envelope, okay. So if k is equal to 2, for instance, that is if there are 2 repetitions of a particular pole, then it is going to be a straight line, or in other cases it will be a polynomial. It will definitely not be as bad as this, but then if it blows up, it is unstable. For all practical purposes, I do not care if it blows up at an exponential rate or if it blows up at a polynomial rate, it blows up is bad enough for me. So that is why we make this distinction. You see, when there are poles on the imaginary axis, if you have non-zero initial conditions, at best they will be oscillatory or they will be held to a constant. If there are repetitions of poles on the imaginary axis, it is unstable. But if you have all your poles on the open left half plane, then they will always decay, and as t tends to infinity, terms like these will tend to 0. So that is why we define this notion of what is called asymptotic stability, okay. Remember, this notion of stability, especially for a linear system, is independent of the input. It totally is governed by the locations of the poles of the system. So if all my poles, and here is a big statement, if all my poles are on the open left half plane, the system is going to be asymptotically stable, right. Remember, this notion of stability we are discussing, again to reiterate, is nothing to do with Bibo stability. In case of Bibo stability, we shall see later, any repetitions or any pole on the imaginary axis, even you do not need repetitions, any pole on the imaginary axis is enough to qualify the system as Bibo unstable. But because we are talking about the zero input response of the system, the stability with respect to zero input, right, with respect to non-zero initial conditions only, we qualify this as asymptotically stable if all the poles are on the left half plane, pure open left half plane, nothing on the imaginary axis. If there happen to be some poles on the imaginary axis and all the rest are on the left half plane and the poles on the imaginary axis are non-repeating, then it is just marginally stable, not asymptotically stable. Why? Because some of the modes, some of the terms like these, some of these signals like these, some of these values, they will not decay to 0 as t tends to infinity. If you have even one pole on the right half plane, on the open right half plane, you can blindly classify that system as unstable. Okay. So I hope that we have been able to relate the poles of the system with the stability characteristics and behavior of the system, right. So it is a very important notion, and I hope that you have been able to absorb this, even though we have not dwelt too long on it. But this we will revisit later towards the end of the course when we do state space analysis. We will again talk about stability and asymptotic stability. Insofar as classical control methods are concerned, where we deal with transfer functions, we are mostly concerned with Bibo stability, in order to define which you actually need an external input, which is to say that Bibo stability, the definition of Bibo stability, bounded input, bounded output stability, requires the presence of an input. That is, you have to talk about the zero state response of the system. Okay. Whatever we have discussed here is independent of the input. It is totally a property. This kind of stability, yeah, is totally a property exclusively of the system. Okay. So in the next lecture, we shall get into actual analysis of circuits, and we will see, when we have actually something very tangible to deal with, how this idea of using Laplace transform helps us in modeling systems that are given by differential equations or integro differential equations. Okay. So thank you very much, till the next time.